Hi friends, welcome to continue following up this channel. So in this video, we are going to do a simple problem, that is problem 104, a maximum depth of binary tree. So actually in the previous two videos, so we looked at problem 2385 and problem 863, right? So for those two problems, we solved them by viewing them as general graph traversal problem. So here we are going to focus more on the structure of the binary tree itself. So because this problem is rather straightforward, so we are going to quickly look at the problem requirement and then we do the coding directly. So for practical purpose or for pedagogical purpose, so we are going to present two formats of solutions. So one format is based on recursion, and the other format is iterative. So I feel that this way it will help the audience to genuinely understand the problem itself. Also can use the thought or ideas here to generalize and to solve more problems. So without further ado, let's look at the problem digest. So here we are given a binary tree. So we want to find its maximum depth. So here, the definition is important. Basically, it's a convention, right? A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node, right? So for example, in example 1, so the longest path can be 3, 20, and 15, or 3, 27, right? So the length is 3, so the maximum depth will be 3. Actually, in some textbook, we define the depth or the levels of a tree is the length of the longest path. For example, if you count the length, so it will be one less, right? For example, this root from this path from root to leaf is 3, 20, and 7. The length is 2 because we have two edges, right? Similarly for the path from 3, 20 to 15. Right. So this is just some notational conventions, but you need to make it clear when you solve such problems. So though it's easy, we need to pay attention to such small details. So with that said, let's also look at the constraints. The number of nodes in the tree is in the range given by the closed interval 0 and 10 to the power 4. So 0 means that the tree can be null. So if the tree is null, so we need to return 0. Because we have no nodes in the past, in any path. And the node value is in between negative 100 and positive 100. But you know, we can have 10 to the power 4 nodes, and we have such number of range. It means basically that the nodes has values that are not unique, right? So with that said, let's look at the coding. So for the coding, I'm going to first write a solution based on recursion. The reason we think of recursion when we look at problems involving binary tree is due to the fact that this binary tree or tree itself is can be defined recursively, right? So for this, let me first write some base condition. Let's recall that if you want to write some recursion, there are 3 conditions. First, you write some base cases, and then you do self-call. And then in the self-call, the cases should walk towards the base case, right? So let's first look at base case here. If not root, I'm going to return 0. So though in this problem, the tree itself is not null, but it can be null. Even if it's not null, we should write this one because it's we need to use this base case. So this is the one case. Another case is that we need to know the maximum depth, right? So then we check if not root left and not root right. So in this case, it means that this tree is a single node tree. So we just need to return 1. So this can be regarded as another base case, right, or stop condition. And then we are going to do self-call and then walk towards the base cases. So we are going to return. We contain the self-call inside the return statement. So now we have the root, because after this two ifs, the root must have subtrees or subtrees. So in this case, we have 1, this counting the root node. And then we want to count which subtree has a larger maximum depth. For example, in this example 1, so the left subtree has a depth 1, and the right subtree, rooted and 20, have depth 2. So we need to return 1 plus 2, right? So what we are going to do actually return the max, right? So self max depth, so we call root left. So notice that because we have read these conditions, we know if root left is empty, this will give us 0, right? Similarly for right subtree, max depth and root right. So another case is that if the left subtree or right subtree is a single node tree, for example this one, it will just give 1, right? So in this problem, so here corresponding to 1, and here corresponding to 2, right? We return 3. So this is one way to solve this problem. So essentially you can see, if not root, if we return the root empty list, and here we return root, and then we return root plus this 1 plus this is nothing but traversal, right? But here we adapt to the problem logic, right? So actually it's beneficial if you analyze the simple problem using some general methods, so you know you can practice how we can use algorithms to specific problems. So before we move forward, let's do a test. Yeah, it passes on one example. Now let's look at a generic case. So this is the one way to solve it. So here I'm using recursion. So now I can copy this one, and I'm going to write one solution based on traversal, but use iterative format. This is also straightforward, but it's good to analyze it. So here, first I'm going to do, let's see, if not root, I'm going to return 0. This is very natural. And then we're going to initialize a, say, stack, or if you initialize stack, you're going to correspond to a depth first based traversal, or you can initialize a container using queue as corresponding to breadth first based traversal. Let's use stack here. So we stack. So we start from the root. So root has just one node in this path for now. So this so basically what we store is node and length or number of nodes from root to this node, both inclusive, right? So root to root itself, just one node. So this one. So we just return the maximum 1, right? So basically, this if we do nothing, do not take into problem logic here, it's just a traversal. But now we want to take the problem logic. So here we stack a pop. So this gives us the node and the length, or the number of nodes. If you can use length, or you can use n nodes. It's also very suggestive. You use n nodes. That's also good naming convention, right? So here we can do this. We can always do this. Max. So let's initialize a result. So the result will be 0. So counting the number of nodes. So we're going to update the result and length. And then we are going to look at node left or node right. But here I want to look at node right. So this is important if we want to say do post-order traversal, right? We need to first check node right, and in other words, the right subtree, and then we check left subtree. So here we check node right, and then we're going to stack append. So node right. So the length would be incremented by 1 because we now including this node. So this is one. Another one is which we can copy that. We change right to left. So let's change this to left, and this to left, and then we're going to return the result. So let's first do a test, and then we make some comments. Yeah, it passes one case. Now let's look at the generic case. Yeah, it passes all the cases, But you know, for this problem, this is not optimal because we don't need to make comparisons for this one for every node. We just do comparisons for leaf nodes, right? Because leaf nodes for sure have corresponding to the possible maximum length. So we just say if not node left and not a node right. This means the node is a leaf node. Then we update the result state. Then let's do a test. Yeah, it passes all the cases. So another thing is to notice that, so this order here is also not essential. We can copy this part and comment out and put here. And then do a test. Yeah, they passed all the cases, but let me recover the original order. The reason here I put node right before node left, because if we think of traversal, if you first check the right subtree and then left subtree, this corresponds to post-order traversal. Let's see what I can do. So here, besides I return this result, I want to also return the corresponding nodes values maybe. So let's see, I can see aux is a list, right? So then each time I'm going to aux append node value, right? So I can print out this aux. So let's do a test. For this tree, right? If you do post-order traversal, what you are going to so here, let's see. This is the pre-order traversal. Sorry. So if you do pre-order traversal, what you get? First you visit 3, right? Then you do left subtree, you get none. And then you visit left right subtree. Because you are doing pre-order traversal, you visit 20, right? And then you visit left subtree 15, and then 7, right? So this is an important point to notice. But if you change this order here, let's see, copy this part. And then comment this out. And then you test that. You say you first visit the 30, and then you visit this one. And then you visit right subtree, and then you visit the left subtree, and then you visit none. It's sort of, it's still sort of pre-order traversal, but not in a traditional sense. You can switch the right and left, right? So if you see it, you regard left and left, right and right. So this is not the standard pre-order traversal, but you do a switch, and then this also pre-order traversal. But you know, in a rigorous sense or in a plain sense, so this way you check first the right, and then do the left. This corresponds to pre-order traversal. Yeah, sometimes I just miss speaking is post-order traversal or pre-order traversal. Actually, we have a playlist, I guess, or a list contains lots of problem on traversals. So this is another solution. But you know, when I do this problem, I think another solution, that is level order traversal. For example, you see this is level 1, this is level 2, this is level 3, then you return this. Let's do that. So here I'm going to copy this one again, and then I'll do this. I'll change this one to be version v2. And here I want to write another level order traversal. So let me first write level order traversal, and then we just add the problem logic, right? So here, let me make some notes. First, write level order traversal in a vanilla fashion. And then we add problem logic. So I guess this way it will help you better understand the thought process. So here, if not root, I'm going to return an empty list. So here, you know, I just do not return integers. The reason is that I just want to write level order traversal. And then I'm going to have a level, let's see, as a root, right? Then what I'm going to do is, so let's see, I have a result. So basically, let's call it level. Well, level. What I'm going to do is I have a temp list. So it just gets the node values. So node value for node in level, right? So then I extend this result by the current temp, and then I update level. So level is going to be, so node, say child for node in level, for child in, say, node left, node right. So here you can use a tuple, you can use a list, doesn't matter. So here, like, let me add a filter if child, right? So as we do this, we update this level, right? As long as the level is not an empty list, so we're going to have the while loop continue. So finally, we just return the result. So we are going to get 3, 9, 20, 15, 7. Let's test that. So here, in order to, I don't want to return. So let's see, I just print, right? Print the result, and then I return 0 because the function signature returns an integer. Let's see. Right, so we have 3, 9, 20, 15, and 7, right? So that's right. So now, how do we get the problem logic? So here, we don't need to retrieve this result, right? Just delete that. So originally have a level. So let's see, we have result 0, right? And then here, we don't need to extend. Now we change the nature of the result. The result now is a counting variable. So thus the level is not empty, so we're going to increment by 1. So in other words, we count the number of levels rather than look at a specific path. This way is not very most optimal, but it's still a way to solve this problem. So, but I don't need to just return the result state. So this method is based on level of the traversal. Let's do a test. Yeah, it returns 3. So if you try this one, you're going to get 2, I guess. Yeah, so because the number node is not that large, I guess this will pass. So let me see if I change this one, version v1. Yeah, so let's test. So here I just return 0. Yeah, it passes all the cases. So that's basically about it. I guess the video is long enough. So originally we promised to present 2 formats. So one is based on recursion and one is based on iterative format. But here we also just in extra we add a level of the traversal. So it's just for practical purpose. So overall, as you look at this problem, so it's actually very beneficial to analyze the problem using different algorithms or different ideas. So with that said, I guess that's it for this video. Thank you.